All right, guys, so this is our last example in section 8. And with this example, we conclude section 8 and also our review for the logic part. And so here's the theorem. It's an if and only if theorem. Not P implies Q, if and only if P and not Q. So how am I going to prove this? Well, because this is by conjunction, I am going to separate it into two parts. So part 1 is going to be this implies this, because this is easier. So the order doesn't matter. I mean, which one you prove is irrelevant. And then part 2, this part implies the second. All right, so I'm going to prove them separately. And then once I prove them, I am going to use the by conjunction rule and we'll say, well, this if and only if statement is therefore true. All right, so part 1, I want to prove this. How do we prove a conditional statement? Well, we assume the first part and then show that the second part is also true. So I'm going to start with assuming P and not Q. All right, so this is assumption for conditional derivation. In this case, I'm not looking for contradiction. All I want to reach to this conclusion. However, this is an and sentence, so that means P must be true. This is simplification of line 1. And also not Q must be true. This is simplification in line of line 1. Sorry, again. So let's write them down. I don't know if I'm going to ever use them, but let's see. So that's it. I'm stuck. I want to show this not P implies Q. How am I going to do that? Well, I am going to open a new box because I'm going to deny my conclusion and assume it is false. So not P implies Q is true. So I'm going to make assumption for indirect derivation. So I am looking for some contradiction in this box. So simple it is. This is a double negation. So P implies Q must be true. Double negation of line 4. All right. So now I can use line 2 and line 5. So Q must be true. This is modus ponens of line 2 and 5. All right. So once I have Q, remember I had not Q. So let me just repeat this. Not Q. So this is repetition of line 3. So I have a contradiction that I was hoping for. So that's it. So this sort of conclusion or assumption cannot be true. Therefore, its negation must be true, which means in line 8, not P implies Q is true, which is my conclusion. Not P implies Q must be true. All right, so that's it. That is the first part. Now I am going to start the second part. Oh, this is, sorry. This is indirect derivation between lines 4 to 7. All right, and then here in line 9, I'm sorry, I just write my conditional sentence. If P and not Q, then not P implies Q. So the first part is true, basically. This is conditional derivation, conditional derivation of the arguments between 1 to 9. All right? Now I am going to prove the second part of the theorem. So part 2. One thing I would like to remark. So in part 2 of this proof, can I use any of those lines? Well, first off, I cannot use any of those statements because all these statements are true under the assumption that the line 4 is true, but I know it is false. So I can't use any of those. All right. What about 1, 2, 3, and 8? Well, when I am in part 2, I cannot use any of those either. Why is that? Well, because everything here depends on the assumption that P and not Q is true. Remember, maybe it is false. If it is false, I know that this statement is true. All right? So everything from line 1 to 8, nothing in line 1 to 8 is usable in my part 2 and for the rest of the proof. The only thing I can use is line 9. Why is that? Well, because everything between line 1 and 8 relies on the assumption that P and not Q is true. All right? So if this is false, none of those lines up until 9 is true. They all are false. Hence, I cannot use them. But what about this statement? Well, this statement is always true, which is what I've shown, right? If this statement is true, I know that this statement is true. If this statement is false, I know that this conditional statement is true anyway. So therefore, although these lines are all potentially wrong, this line is always true. So therefore, for the rest of my proof in part 2 and if it continues in part 3, whatever, I can use only line 9. All right, that's very, very important. So therefore, I normally don't want to erase it, but because I don't have a long board, I am going to leave line 9 and I'm going to start part 2 here. All right, and this is line 10. I'm going to prove this statement. So as usual, I'm going to start with the assumption P implies Q. What if it is true? I need to show that this statement is also true. P and not Q. All right, so how am I going to show that? From this, I can't derive anything. So this is assumption for conditional derivation. Very good. So line 11. I'm going to negate. I'm going to use indirect derivation. So I'm going to assume that not P and not Q is true. All right. So indirect assumption for indirect derivation. Very good. So what else do I need? Okay, so you know what? I need to get a contradiction with something in line 9, 10, and 11, all right? All the other lines are useless, I know that. Okay, but it doesn't seem like I can get a contradiction here, so maybe I should keep assuming, keep proving some other conclusions. So conclusion that I'm going to prove, for example, can I show that P is true? All right. Why? Why do I want to show that? Well, if I show that P is true, and if I show that not Q is true, well, then I can show that P and not Q is true. And so I contradict with this one, which is the contradiction I was looking for. All right. But you know what? I can use a trick. What is that trick? Theorem 1. I call it Theorem 1, but this is the theorem we proved already. Remember, it says, hey, look, if you're taking the negation of P and Q, all right, it is equivalent to not P or not Q. So the structure here is very similar. So you know what? Not P and not Q is therefore, I just distribute this negation over, so it must be not P or not Q. So this is thanks to Theorem 1 and line 11. Hope this is clear. So instead of proving this conclusion or this one, I can actually use the theorems that we already proved as a shortcut, like the inference rules. All right, so every theorem is an inference rule, in fact. Okay, very good. So I have this. All right, what benefit do I get out of this? That's a good question. So I have not P, I have not Q. Okay, so you know what? It seems like I can use MTP. For this, I need that P is true. All right, so the conclusion I want to prove is that P is true. Okay, or but if P is true, that means I'm going to assume for indirect derivation, I'm going to assume not P, but if I assume not P, I'm not going to be able to use MTP. So therefore, I like to prove this conclusion. I hope you're seeing sort of the way my thinking process evolves. So if I aim to prove this, not P, by indirect derivation, I'm going to assume not P, so it's going to be P. So here I have not P, here I have P, so therefore this must be false, so this is going to be true, so Q is going to be true. And we'll see where I can go from that on. So I am going to make another table because this is subproof of a subproof. So line 13, I am going to assume not P. All right, because this is the conclusion I am hoping to reach. This is assumption for indirect derivation. I am looking for a contradiction. So line 14, this is P. This is double negation of line 13. All right. Once I have P, I have not P. So what does that mean? So P is true. Therefore, not P is false. So this is false, but this statement is assumed to be true. So therefore, this must be true. So 15, not Q is true. Well, this is MTP of line 12 and 14. So line 16, this is equivalent to Q. This is double negation of line 15. So what do I get? Okay, so I have P true, I have Q true, then I have P implies Q true. Is that clear? Right? I mean, this is right. I mean, if you remember the truth table of the P implies Q, when P is true and Q is true, well, then the P implies Q must be true. All right. We don't have a name for this rule because this is how we defined the truth table of P implies Q. So therefore, therefore, that's it. I'm going to leave it blank. I don't have a name for this. But in line 18, I think I got my contradiction. I already had assumption P implies and not P implies Q. I just repeat line 10. So I have a contradiction. Okay, very good. So this contradiction tells me that given all these assumptions are true, this assumption cannot be true. So it must be false, which means not P is 19. Not P is true thanks to indirect derivation between the arguments 13 to 18. So not P is true. Okay, so let's repeat. I started with this assumption for indirect derivation. I want to show that not P is a correct statement under the assumption in 10 and 12, which implies 12, thanks to Theorem 1. So if not P, so this is the negation of my conclusion. So if not P is true, well, the double negation of this line means that P must be true. If P must be true, that means not P is false. But because this statement is true, therefore not Q must be true. So this is MTP basically. And if not Q is true, then Q must be true. This is double negation. And finally, because P is true, Q is true, truth table of line 14 and 16 implies that P implies Q must be true. I'm just repeating line 10, because not P implies Q is also true, but these two statements cannot coexist. Hence, I have the contradiction. That means under those assumptions, not P cannot be true. So not P must be true. Okay? So I can no longer use these arguments for the rest of my proof, but I know that not P is true. So what does that mean? That means P is a false argument, right? So that not P is a true argument. So if P is a false argument, well then P implies Q is always a true argument. Well, again, this is truth table thanks to our argument 19. So whenever P is false, P implies Q must be true. All right? Once again, I'm not taking or borrowing this from line 17. I derive it by using the fact that not P is a true statement, and hence P is a false statement. So therefore, I can just repeat line 10, not P implies Q. All right? So I just repeat line 10, and so what I have is a contradiction here. All right? And so in this contradiction, I basically show that my assumption in line 11 cannot be true. So therefore, in line 22, let me write it here, I must have P and not Q is true thanks to indirect derivation between the arguments 11 all the way to 21. All right? So P and not Q is a true statement. So what I have shown in line 10, if I assume that not P implies Q is true, which is the first part of this conditional statement, then P and not Q, the second part of the statement, must be true. Hence, I actually have proven this part too. So I'm going to erase all this. So I'm going to call it line 23. Let me just erase this. So in line 23, I basically have the following: not P implies Q implies P and not Q. All right? So this is thanks to conditional derivation between line 10 all the way to line 22. So finally, in line 24, remember P if and only if Q is equivalent to P implies Q and Q implies P. So in line 23 and line 9, I basically show that. So I can conclude that not P implies Q if and only if P and not Q. All right? So what is the property of, what is the name of this rule? It's by condition. So by condition of line 9 and 23. And hence, this is the conclusion of the proof, or the end of the proof.